Welcome to our class today. It's an introductory class on the design of structural steelwork to standard British Standard 5950. And design of structural steel is not something that is new to you because you did that at your diploma level, I believe. So some of the things will be direct. For example, some formulas that you obtain from structural analysis. The formulas, some equations that you obtain from structural analysis will be very key here. Let's get straight to it and see that we are saying that the aim of structural design is to provide, with due regard to, is to should be provided should be to provide with due regard to economy a structure. Okay, so you want to design a structure that first of all is economical. That is the first consideration. Economical. You first consider the economy. And when we talk of economy, we are not only talking about economy of monetary. Okay, we are also talking about economy of space. We are talking about economy of material. Okay, it's not only economy of money, but economy of space. You don't want to have something that is consuming much space, yet you can have something that is consuming less. Economy of weight. Also want to consider economy of weight. You also want to consider economy of material. Yeah, you don't need to use something that will use a large number or size of material, yet you can use one that is that can consume less materials. Okay, so the balance line of monetary, of course, the more, yeah, the balance line of space, economy of space, economy of weight, economy of material. Because yeah, you can say you want to use a strong steel, okay, but it is heavy, and yet you do not need that one. You do not need that particular weight. Okay, because when you talk of the weight of the material that you use, you're talking about some dead loads. You're talking about dead loads. So the more the loads, the more the dead loads, the more cumbersome the structure becomes. So in fact, nowadays we are moving to what you call lightweight design. Lightweight design. Yeah, we have come to see that it is not necessarily that something that is heavy is strong. It does not necessarily mean that. So you can have some lightweight materials that are still strong. Yes. So we are saying that the aim of structural design is to provide with due regard to economy, and the economy and those factors that I've spoken about, a structure that is capable of fulfilling its intended function. Also sustaining the specified loads for its intended life. Okay, for its intended life. So we are saying that it should facilitate also safe fabrication, meaning you want to modify. You should modification and also manufacture, because you realize when you talk of steel, sometimes we cannot produce steel that have some certain shapes. Okay, so we might be limited to now want to modify, maybe by jointing, bolting. We might also want to do welding. So we cannot work with something that cannot be welded or that cannot be bolted. Okay, the design should provide for safe fabrication, also provide safe, easy transport, easy handling, and also easy erection. So it should take into consideration the need of future maintenance. You don't design something that you will not be able to maintain. Okay. It's like you are digging a borehole and you don't know how you are going to get out of the borehole. Yeah, just digging, digging, digging. You don't know how to get out. It's good to, before you start an aeroplane, you need to know how to stop it. Okay, so that is one of the considerations. You should take into account future maintenance, final demolition. If I want to demolish, how can I bring this structure down? Am I building a structure thinking that this place I cannot shift, I cannot do what? Recycling. If I demolish, how am I going to, how can I reuse this material? How can I use it again? Yeah, and we recycle. How can I take it? Maybe can I take it back to the factory and can I use it again, reusing all materials? So structures should be designed by considering the limit states. So this is from the British Standard. When you consider British Standard, the British Standard uses a philosophy that is called limit state design. Limit state design. Yeah, limit state design. So if it considers limit state design, there are two states that are considered. The first one, you have what we call ultimate limit state. So that's ULS. And then we have serviceability limit state, that is SLS. So we have to consider the limit states. It means we have to think of ultimate. Let me just talk about ultimate. Let me have a new slide here. And okay. So when you talk about ultimate limit state. So we want to consider a situation beyond which a structure will fail. Okay? Beyond which a structure will fail. Okay? Such as fracturing, breaking. Okay? Maybe it can even bending. The state beyond which a structure will fail. Okay? Beyond which a structure will fail. But when you consider serviceability, we're looking at the state that ensure maybe comfort of use. So the British Standard has balanced the two. What would happen if there is maybe vibrations? What would happen in the case of earthquakes? Yeah. So you see, when you talk of ultimate, it's a structure on its own without an external influence. Can it bend? Can it break? Can it fracture? Can it buckle? Okay. But when you talk of serviceability, you're talking about service. How, when, even if the structure has not reached its ultimate state, what would happen if I subject it to certain vibrations, if I subject it to certain situations? So those are the two states. So you should consider, we are saying structures should be designed by considering the limit state beyond which they would become unfit for intended use. By the way, you should be telling me whether you're getting me. But let me log in using this account just to monitor what you guys are seeing. Okay. Yeah.
Mwalimu, can you repeat about the serviceability?
About serviceability. Okay. Good.
Yeah.
All right, I can see. So I'm saying when you talk of serviceability, we are talking about the comfort of use. Okay. usage, because limit state talks about a particular state beyond which a design or a structure will fracture, break, bend, fail. Generally, will fail. But even before we get to that point, what would happen if this place has some use? Maybe vibrations, for instance, vibrations. When maybe you're designing a workshop, you consider things like vibrations, things like earthquakes, and many more that we are going to see. Those things, even if the structure has not gotten to its ultimate, it can still affect. Okay, it can still maybe repackage. It can do, if it was concrete, it can do repackaging, or maybe it can ensure that maybe it can make the bolts loose. Okay, so what design can we adopt that will ensure that we are still comfortable when we are using it, but still we are still uh, within the limit state of it has not gotten to the point of bending, maybe breaking, fracturing, buckling, as we are going to see. Are we together? Who was that? I think Nicholas. You get my point.
Yeah.
Yeah. Okay. That's good. So that's why we are saying that design should consider those limit states beyond which they would be unfit for their intended use. Also, we have what we call appropriate partial factors, or these are what we call factors of safety. Okay, should be applied to provide adequate degrees of reliability for ultimate limit states and serviceability limit states. So, those factors of safety, which we are going to see throughout, this is just the background, which we are going to see throughout design, they should cover, they should cover, they should provide for this safety, these states. Yeah, because if you just consider maybe the weight of the building, if you just consider the dead loads that they are without adding a particular factor of safety, you have not given it a room. It's like if you want to tie a knot and you know you need 1 meter, okay, provide exactly 1 meter, then any small mistake or any variation will leave you no room to make adjustments, or unforeseen situations. Maybe of course, I know some of you have computers. Ukinunua computer iko inapiga kelele, but after a while you didn't intend, but it now starts uh, having a lot of noise. So machines are that way, structures are that way. They can behave in a particular way that was not factored in. So it's important to introduce factors of safety that brings both. Somebody wants to join? Okay, that brings both. That brings both aspects of serviceability, and also the aspect of use over ultimate. Yeah. So we are saying that ultimate limit states concern the safety of the whole or part of the structure. Is it safe? Is it safe? Okay. Okay. Is it safe? Is it safe? So it means uh, because if it fails or if it fractures, then it's no longer safe. Okay, it's no longer safe because you will just die. But serviceability, you might not die, but you will not be comfortable there. Staying in a room that can swing, or something that has bent, has deflected. Okay, something that has deflected. When there is wind, you can feel that, hey, all those sounds. So it is still within the ultimate limit state, but it's not within serviceability. So we are saying it corresponds, serviceability limits correspond to limits beyond which specified service criteria are not met. Service criteria are not met. So when you talk of, just have a look at this table that I have identified, talking about limit states. When you talk of ultimate limit states, somebody wants to join? Nicholas. Ultimate limit states. The first one we'll talk about strength. Okay, is it strong? For example, just try to imagine a 50 kg boy lifting 50 kg boy lifting a 100 kg bag. So can we say this boy is strong? Is he strong? Maybe somebody can tell me if the boy is strong. Who? Nicholas or Tom?
No.
The boy is not strong. Sindio?
He is not strong. Yeah,
What?
he's
I
not
cannot
strong.
see it.
You cannot see it, Nicholas?
Yes, I think I cannot see your presentation.
Tom, can you see my presentation?
No, siweziona mwalimu.
Wow. And I'm seeing, wow. And now I think you can see it.
Yeah, for now I can
Very
see.
clear.
It
Good.
is very, very clear.
Thank you. So we are talking about the balance between strength. So if the boy is 50 kgs and he wants to lift 100 kgs, the boy is not strong. But if the boy is still 50 kg and he wants to lift 40 kg bag, is the boy strong? Yeah? Nicholas?
Yes.
So the boy suddenly becomes strong. So it means that strength is relative depending on that which it will handle. Okay, so we cannot say this building is strong or not. So we can only say that it is not strong. It cannot hold this load that we want to apply. And as long as the load exceeds the design strength, which is 50 kg, the structure is unfit or is not strong, is weak. It cannot hold that load. That is why we are saying it is part of the ultimate. If it is exceeded, if it is 51, that it is beyond, it is unfit. It is unfit for use. Yeah, but if it is 50 and the weight is 40, then the structure is okay. Okay, so we want to design structures. We don't want to design strong structures. We want to design structures that can hold a particular load. If the load is 100 kg, then I design a structure. What's happening? Then I design a structure that can hold 100 kg, and that is when I can now say that that structure is strong. So strength, including yielding, rupture, buckling, forming a mechanism. Yeah, we are going to talk about this, forming a mechanism. You will see when I talk about continuous beams. So it can fail by yielding. It can fail by rupture. Yielding means you have subjected it to more strain until it becomes plastic, as you will see. Rupture, it can rupture, it can buckle. Okay, so all these are ultimate limit states. The other one is stability against overturning. So sway stability. Okay, sway stability. If I know when we are talking about retaining walls, as at some point in your structural analysis, we said that if you have a particular retaining wall, and this retaining wall can hold up, is subjected to a particular force that is beyond its FD. This is D. Okay, so each retaining wall, maybe this one maintained by its own weight, the weight. So it will offer a particular resistance to this force. But if this force is more than what this retaining wall can offer, then there's nothing we can do. There's nothing we can do. It is unfit for use. That's another thing we consider. Is it stable against overturning? That's the other thing, overturning and maybe sway stability, fracture due to fatigue. Okay, due to as a result of continuous use, steel can fracture or steel can brittle. Okay, you realize that it can form some thin lines, which is in other words, you will also see how that relates to yielding. And when you talk about serviceability, deflection, when it deflects, a steel structure can deflect like this. Okay, can deflect like this and stay like that even for 10 years. So yeah, it has not been exceeded. Yeah. The strength is still okay. It can still hold, but one say, can you really stay in such a building? It is not fit for use. It is not fit for use. So deflection will be part of serviceability, vibration, yeah, wind-induced oscillations, and maybe durability. All those will some of the things that we consider when we are designing using the limit state design philosophy according to British standard. Are we together? Are we together? Nicholas? Awesome. That's good. We proceed. So, in checking, when we want to check the strength of a structure, so we are saying that the specified loads, okay, if you have maybe dead loads of maybe 10 kilonewtons, and live loads or maybe 16 kilonewtons. We are saying that we don't use them the way they are, because if we use them the way they are, we have not factored in those aspects of serviceability and ultimate. So we are saying that it should be multiplied by relevant partial factors F given in table 2, as you are going to see. This is table 2 according to British standard. I already sent you the British standard 5950. This factored load should be applied in the most unfavorable realistic combination for the part or effect under consideration. So we don't consider the best case scenario when we are designing. We consider the worst case scenario. What is the worst case scenario that this thing can happen? It can fail by deflection. So we design against that failing by deflection. We design against shearing, because the worst case scenario is that it will shear. There you get. So we say that we consider the most unfavorable realistic combination. Okay, so for building without cranes, you realize that in steel structures, when you're rising higher and higher, you can use the same structure to hold the cranes. But for building without cranes, which is mostly used, we find that maybe you can have dead loads and imposed loads as a one combination. You can have dead loads and wind loads, or you can have both dead load, imposed loads, and wind loads for buildings without cranes, which we are going to consider. Okay, so we are saying, where's the table 2? Let me give you the table 2. This is the table 2, table 2 from BS5950. It has more. It has more. If you check, this is just an extract. So dead load, the factor will be 1.4. Dead load acting with wind and imposed, that's 1.2. Dead load whenever it counters the effects of other load, that's 1.0. When retaining, sliding and overturning or uplift, in other words, you are saying that if the sliding force is 20 kilonewtons, then you just need another load of 20 kilonewtons to cancel off. Okay, because if you now provide this one which is 25, it will be it will be the other way around. So we don't provide, the factor of safety for uplift and overturning should be 1.0. Okay, should be 1.0, because any increase, or maybe if you make it a fraction or something else, it will now slide the other way around. So you provide a force that is equal to that magnitude by which it is acting against. So imposed loads 1.6. So this is, for instance, combination 1 would be 1.4, dead load 1.6, live load. We have imposed load acting with wind load, that's 1.2. We also have a wind load is 1.4, storage tank including contents 1.4, storage tank empty when restraining sliding. Anytime it's restraining, sliding, overturning, or uplift, we use 1.0. So still going to see how we go about that in designing. So I think this one you just study on your own. The parts of BS5950. What does it entail? These are the 9 parts. I don't want us to go into depth about all this. So talking about the properties. Now these are properties of iron and steel. Properties of iron, because we want to start with the design of steel. So we are saying, if you look at this diagram, if you subject a steel rod on a load, if you set a load on a steel rod and it is fixed on one end, what will happen? There will be a change in length. There will be a change in length. That change in length will cause something that is called strain, where strain is the change in length over original length. This is strain. And then we have now stress, because this load is acting on a particular area. Stress would be the load newtons divided by the area, which is cross-sectional area. When a graph is plotted of stress strain curve as shown below, you'll realize that steel will respond in this manner. Okay, steel will respond in this manner. So you will have it will first of all increase linearly up to a certain point called yield point. So steel will yield slightly at 355 newtons per millimeter squared. You're going to see the relevance of this. So what we will design, mostly we'll consider 275, this one 275, because it is still within the elastic limit. We'll have 355, and then we also have 460, which you will see how we will approach that one. So we are saying that it will increase linearly. And when it increases linearly, we say it obeys Hooke's law. Where stress is directly proportional to strain, and at least up to the point where elastic limit is exceeded. So here we say that steel is elastic. Okay, and here steel is plastic. So steel here is elastic and steel here is plastic. So we don't want to only design for steel when it's elastic. We also want to design for it when it's plastic, because not unless it has failed. This is the point of failure where we don't want it. Naona hapa ndo hatutaki. Hapa hatuna shida nayo. We don't have an issue with this. We can design for plastic. We can design for a plastic situation. We can also design for an elastic situation, but we want to say that we cannot allow it to get to this point of failure. this point of failure. So most people play safe when we use 275, as we are going to see, we are going to see. So we want to design for both situations, both elastic and plastic ranges. As you have seen here, this is the elastic range, here to here, elastic, this here to here is plastic. This is plastic. Yes. We still pamoja. Let me see you guys. Tuko pamoja. Nicholas, okay. Tom ameweka simu akatoroka. Okay. Kasema mwalimu ajiongeleshe. Okay. So, we have 3 basic grades of steel when they are manufactured. The first one is S275. The second one is S355. The third one is S460. These ones, they will vary also in thickness. They'll vary in thickness, both of the flange and the web, as we are going to see. We tutaona side design how it is. Okay, so they will vary in design. So we have S275, S355, S460, and grade S460 is the strongest. But the lower strength grade S275 is mostly commonly used in structural applications for reasons that we will see in calculation. So S will stand for structural, and then the number will indicate the strength of a material. And I want to say this now, that a material is as strong as the stresses it can bear. Okay, stroke loads, reactions it can resist, stresses it can bear. So if we say that ILS S275 is this is the strength Newton per millimeter squared, it means it can resist up to 275. It can bear up to 275 Newton per millimeter squared stress. Okay, so the most commonly used sections are UBs, universal beams, and universal columns. Some of the physical properties that we will see here in a few will be, we have the principal dimensions, we have area, we have second moment of area. Hizi vitu zote I know we calculated in properties of sections. Properties of sections. We have principal dimensions, area, second moment of area, radius of gyration, elastic and plastic section, modular, section modulars, and they have also been tabulated in BS, which I have brought some of the images here for us to see how to go about them with their conventions, right here. Okay, so let's look at this. Let's analyze these images. So let's look at case A. So T, this is what we call the flange. This is what we call the web. Okay, that's what we call the flange. This is what we call the web. So the thickness of the flange is T, and the thickness of the web is small t. It's important for you to know that. Hizi ni vitu tutakuwa tunatumia sana. Wow. Yeah. So we also have other parameters. So it's important to know this is the flange and this is the web. This is the web. So these are beam, universal column. So some of the properties we want to see, we have B, we have B, okay? B, see B go up as total from here to here is B. Half of it is B, and realize it's center to center, so it cuts within that axis. Okay, then we have B, we have D, we also have D. Okay, so D is from, it's only the one for the web, the length of the web is small d, and the total length will be D. We will also have L, which would be the span. Okay, maybe we can just now look at some of these parameters here in the geometry. So we have, sorry, B, so we have B is the breadth of the section. The breadth of the section, B, this one, is the breadth of the section. Okay, you can draw that one if you if you can. B is the breadth of the section, and we have B is here. B is the outstand of flange. Outstand of flange. In other words, it's half of B. It's half the breadth. So let's just write here outstand. Outstand of flange. Outstand of flange. So D will be the depth of the section. D is the depth of the section. And then D, the small d, is the depth of the web. So this is the depth of the section. This is the depth of the web. The depth of the web. What else? L will be the span. L is the span. L is the span. Where is it? L is the length of span. So how long? Why have they not shown us here? But L is here. How long? How long? L is the length of span. L is the length of span. The rest, oh, we have what? We have T, small t. We have talked about it. Thickness of the web, thickness of the flange. Nini ingine tutataka? DDT. YY section, YY. XX is XX. Symmetry. What else? I think that's okay. Are we together? Yeah?
Yeah.
Okay. Okay, let me see. Okay. All right. We proceed. Let's proceed. So this is a universal beam. This is a universal column. Okay. This is a channel section. These ones can either be manufactured this way. They can either be manufactured because easy milling, or we use it mostly. These ones can either be manufactured or jointed. Okay, they can be manufactured or jointed. Or jointed. These hollow sections, rectangular sections, all these other sections, they are important sections. We will first need to establish how to design for this, and then design for jointing and bolting. We'll design for jointing and bolting. Okay. So we proceed. So some of the things that maybe we have not identified in those diagrams. The first one, we have area of the section will be denoted as A. Gross cross-section area of the steel section, AG. IXX and IYY, you talked about that, is the second moment of area. Sorry. Second moment of area. A radius of gyration about the major and minor axis. We have plastic moduli, which is both at section XX, major and minor. Okay, XX being major, XX, and then this YY. T, thickness of the flange, T, thickness of the web, U, buckling parameter. What else? Z. Z is elastic modulus. So S is plastic, Z elastic. What we have I, XX was second moment of area. Very important. Plastic modulus, elastic modulus in major axis, major junior X, major axis. Also we have major axis. What else have I not talked about? R, yeah, R, X and RY. Rx and Ry, this will be the radius of gyration. Somebody is kindly unmute, Tom. That will be the radius of gyration, which will also be identified from British standard tables. You will not need to calculate the radius of gyrations, but each geometric property will have a particular pre-calculated radius of gyration. Okay. We make progress. These are some of the things that we'll find when we are doing bending. AV will be the shear area. BL, stiff bearing length. E, you should know this one. Elastic, modulus of elasticity, which is stress over strain. Force tensile, force shear. V, mostly where we use V, we are talking about shear force. So FV will be shear force. Okay, shear force. AV will be shear area. LE, very important, effective length. We will see effective length, and the rest are also very important. M being one of them, design moment. MC, moment capacity. So there's some point where we'll say that we want to check which one is greater than which one, to confirm which section we are going to take. Okay. All right, and many more. There are many others, but just to mention something that is important, here we have PY. We'll use it so much. It is the design strength. Design strength of steel. Then we have something else that's very important, is deflection. This is deflection. We'll see that when we are designing against deflection. We have this constant, elastic constant, which will be the root of 275 over py. You will see how this one is applied. Yeah. We also have slenderness ratio. And what else? And many more that we will talk about. Buckling, M buckling. I think that's okay. Compression. We'll talk about them as they come. So, just to introduce introduction to now steel design, there are three principal methods. The first one is simple design. If you guys did maybe analysis of 2D frames, if you did analysis of 2D frames, then in one way or the other, you came to this point where you believed or you assumed that all sections, all joints were pinned joints. Okay, and then you also said the other assumption was loads are carried at the joints. Okay, loads were carried at the joints. Those are some of the things that you assumed in the analysis of 2D frames, that they were pinned joints and then loads are carried at at joints. Okay, they are bared at the joints. Okay, so that's one of the things that we consider when we are doing simple designs. We want to ensure that we provide a way that structures are regarded as having pinned joints and significant moments not developed at connections. So why are not they are not developed at connections? Because they are pinned joints. Okay, if they could be what, fixed joints, then we could have three reactions. We could have the horizontal reaction, we could have vertical, then we could also have moments. But in this case, we are considering that they are pinned joints and that significant moments are not developed at the joints. Consider figure A below. These are figure A. Okay, the structure is prevented from becoming a mechanism by appropriate bracing using shear walls or bracing. Here, these are braces. These are braces. So when you provide braces, they behave as individual systems. So when you provide ukipeana a wind load here, it is going to be, when you supply a wind load at one section, then it will not affect the entire section. It will not affect the entire section. Unlike this one, where no bracing is, then when you provide a wind load, when there is wind load or there is a horizontal force, it will act as a system or as one thing. So it is a mechanism. That's why you call this one. This is a mechanism now. Okay. So we are saying that this is the first methodology of designing. Simple design is regarded as having pin joint. It's important for you to know what we mean by that. Okay, pin joint. So you can have a beam in this manner. Okay, you can have a beam in that manner. You can have a beam in that manner. Like so, this is a pinned joint. These are pinned. These are pinned joint. Okay, the pinned joint. Okay, so we make progress. Let's make progress. Okay, so the second one is a continuous design. The joints in the structure are assumed to be able to fully transfer the forces and moments, okay, in the members which they attach. So in as a transfer, it can transfer, this joint can transfer the moments to this member. Okay, so it causes it to respond in the way that the first one responded. So analysis of structure may be by elastic or plastic methods and will be more complex than simple designs. However, now that we have more systemic, more computerized methods, this has been found is most economical. It's most economical. It's most economical. However, you see, it will require much resources to look at that. You have to either design by elastic plastic methods, which is complex than just simple design, because simple design uses an assumption that might not be the case at all times. It might not be the case at all times, that it does not transfer, that does not transfer moments to the members. Yeah, I just come to think of it, and I think it actually transfers. But yeah, we'll see how that will be. Then we have semi-continuous design. The joints in the structure are assumed to have some degree of strength and stiffness, but not provide complete restraint as in the case of a continuous design. So the actual strength and stiffness of the joint should be determined experimental. So it's a mix, it's a blend of the two the two systems, system A and system B. So those are just um, design methods. So the one that we're going to use mostly will be simple design. At this level, we're going to do simple design of steel. Yeah, simple design of steel. So we have introduced steel design by looking at the methods. I'd also love to introduce steel design by talking about loadings, which we had already talked about, by saying uh, to obtain design loading at ultimate limit state for strength and stability calculations, the characteristic load, that actual load is multiplied by a load factor obtained in table 2, which we saw. You remember we saw a particular table. Yeah, it's actually here. Where is it? There's a table 2 somewhere. Table 1, that's table 1. Table 2. This is the table 2. So using the factors displayed here in table 2. So we are saying, sorry, we are not there yet. So we have to obtain designing loads at ultimate limit state for strength and stability calculations. You multiply the characteristic load by a load factor obtained in table 2. So dead loads will be multiplied by 1.4 as we saw in the table, and imposed vertical or live load will be 1.6, except when the load case considers wind load also, in which case dead, imposed, and wind loads are all multiplied by 1.2, because you saw that wind loads considers 1.2. So to obtain design loadings at serviceability limit state for calculation of deflection, the most advanced realistic combination of unfactored characteristic imposed loads is usually used. We will see how this happens when we are considering deflection, things like deflection, things like what else? We had some other parameters here. Table 1, deflection, vibration, wind induced oscillations. That's how we are going to see how those factors will be utilized. Okay, any question up to there? Tom, any question?
Niko sawa mwalimu, hizi nazo ungetupigia.
Umesemaje? Okay.
Niko sawa, hizi nazo ututumie.
Yeah, you will have them. You'll have them. Okay. So I think with that, I'd love to maybe pause at that. So next time we meet, we're going to talk about design strength, and then we'll proceed to design strength parameters. We do then we now start designing steel beams and joints. Yes, I think with that, you guys, I think we're good. Yeah. So I'll see you I'll see you next week.